Okay, okay. As promised, here's an alternate, slightly alternate anyway, method for solving this first problem. So we want to find the point. We got this applied force here on this spring, which is starting at rest, and we want to find how far it stretches before it comes to rest again. So the way we do that is we say the starting state of the system, I'm going to call this state 1, okay, is when it's at rest initially, and then later on it's stretched out much further, so it's gone a displacement x, and there we go, and now the velocity is 0, and at the beginning of the velocity is 0. I'm going to call this state 2. So what I want to find, and we still got this applied force here. Okay, so what I want to find is the how much time passes, or not how much time, what this distance x is where it's finally brought to a stop again. So the way I do this is I set up my little bookkeeping system where at the beginning I do kinetic energy and I do potential energy due to the spring. That's the kind of potential energy we're dealing with here. And then at point 2 I do kinetic energy and potential energy in the spring. Okay, so initially this thing is not moving, which means my kinetic energy initially is 0. Okay, and initially this spring is not deflected from its rest position at all, so potential energy there is 0. And what that means is that total mechanical energy, which I like to call EMEC, but you can call whatever you want, is also 0, not surprisingly. Plus potential is mechanical energy. At state 2, now it's come to a rest again. So it started, we pulled it for a while, and now the spring is pulled so hard that we've come back to rest again. This is as far as we can stretch it. And actually, it's not at rest, really. It's come back to stop. And in a moment, if we went a little bit past this moment, the spring force would actually start pulling us back this direction. So it's not technically a rest, but it's started at a stop, and then, it started with no speed, and now it also has no speed, and it's about to start snapping back. So kinetic energy is 0. At this point also, spring potential energy is not 0. Spring potential energy is actually 1/2 k x squared, which means total mechanical energy is 1/2 k x squared. So now what we notice here is that mechanical energy is not conserved between these two. These are obviously not equal. 1/2 k x squared is obviously not equal to 0. And the reason is because we've had some work done on the system. Anytime you have mechanical energy of a system being different from one point to another, that means some work is done, which means the work done between 1 and 2 must be the change in total energy, in total mechanical energy, which means it's going to be 1/2 k x squared. Okay, this is your final kinetic or final mechanical energy. This is your initial mechanical energy, so you must have gained 1/2 k x squared mechanical energy. That was the work done. Okay, so now we want to find out, well, the work was done by the applied force A, which is constant, right? So we want to find out what this distance x was over which this work had to have acted. So work done was this constant force A. Since A is acting in the same direction as the displacement, we can just multiply them together, scalar fashion, and not worry about it. So applied force times x equals 1/2 k x squared. And that has two solutions. One is x equals 0, kind of obviously. The other one, if you factor out the x, is that x equals 2 times the applied force over k. And that's the same answer we got using the other method. And I've already plugged that in for my numbers and gotten 0.113 meters, and that was correct. So this is how you would do it using potential energy. And some people find this a little more intuitive, a little easier to understand, especially when you're dealing with when you're dealing with a conservative force. That's the advantage of a conservative force, is you can do this potential energy thing. So there you go.